Okay, YouTube, in this video I'm going to run a brief explanation of how you solve exponential equations using a special property that we call the one-to-one property of exponents, okay? But before we get into that, let's kind of take a look at what it is that we're trying to do here. This is my first video in which we're solving exponential equations, and exponential just because our variable or our unknown is up in the exponent. So how one solves for one of those is very similar, as a matter of fact, to how you might solve for something like this. The idea is going to be that we're going to try to isolate the base of this variable expression. So whatever this exponent's attached to, we want to get this thing here by itself, which would mean if we had an equation like this, we would boot the 6. We're still going to boot the 6 on something like this. So what I'm going to do is I'm going to start by adding 6 to both sides, because the first thing we want to do is isolate the base. Okay, and so you'll notice that this thing that we're solving for here that's up in the exponent, the thing it's attached to is by itself now. I would even say that if you had something out front like this times 4, you would have to clear that out of the way before you could solve something like this. But I'm saying, looking at something like this, now we're in a position to speculate as to what would the exponent have to equal for this to be 16. And you know what I know? I actually know that 2 to the 4th is actually equal to 16, because 2 times 2 times 2 times 2 is really 4 times 4 is 16. And we can actually check this also by plugging it back into the original statement here. We say 2 to the what power minus 6 would equal 10. Well, I happen to know just by intuition alone that this would be 16 minus 6 equals 10, and we get 10 equals 10. So the idea is that we're going to be solving equations like this, but what we want to do is use that one-to-one property that I stated earlier. So we say for any base that's not 0, it's greater than 0, it's positive, and it's not equal to 1, then we say b to the x is equal to b to the y, and then x equals y. In other words, if these two bases are the same thing, and they're not negative, and they're not 0, and they're not 1, then x has to be equal to y. Like, this has to be a following statement here. So what I want to do is I want to reconsider this statement that we, or this equation that we saw up top, and try to solve it again, where I'm still going to isolate the base. Is the first thing we always do here. But what I want to do is I want to notice here, by the way, that 2 has a base of 2. This has a base of 2. What I want to do is I want to rewrite the right side as also having a base of 2. The question is, can I rewrite the 16 as 2 to the something power here? And the idea was that I could write it as 2 to the 4th. So now that I say 2 to the x is equal to 2 to the 4, what we can determine essentially is that these two things must be equal. It follows that x equals 4. So what we did with intuition alone on this last part right here, we are doing now formally by rewriting both sides of this equation as having the same bases. So let's look at one more equation here in which we have an exponential expression. We have an unknown in our exponent here. 4 to the 3x power is equal to 8 to the x plus 1 power. The idea is that I have two bases on different sides, but I could solve this if I could rewrite both sides as having the same base. And I noticed that 2 would be a common root of this. Or in other words, 4 is a power of 2 and 8 is a power of 2. So what I'm going to do is I'm going to rewrite both sides. I'm going to say that this thing, which is a power of 2, is equal to this thing, which is a power of 2, and they're both being taken to their respective exponents here. Except for we said that 4 is really 2 squared, and 8 is really 2 cubed. So to solve something like this using the one-to-one property, we're just going to use our rules of exponents here that would say that, you raise a power to a power, you multiply these two things, and we get 2 to the 6x now. And on the right side, we get 2 to the 3 times x plus 1 is 2 to the 3x plus 3. And so now that we have this rewritten as both sides having the same bases, then we could say, since they're equal, then these two expressions here must be equal. It has to follow by the one-to-one property that these things are equal. So now we're just going to solve this like we know how to do. And a few step equations. We say 3x equals 3 and x equals 1. And the last thing I want to do here is I want to say, is this a solution value? And remember, solutions, when you plug them back into the original statement, give you a true statement here. So we say 4 to the 3 times 1 power is equal to 8 to the 1 plus 1 power. And so we get 4 to the 4th is the same thing as apparently 8 to the 2nd. So we get 64 here on the right side, and 4 times 4 is 16. Actually, let's see here. If I plug this back in, we got 4 to the 3rd. Sorry, this is 3 times 1 here. This is a 3. And that's much better because 4 to the 3rd is 64. So we get 4 to the 3rd is the same thing as 8 to the 2nd. But that's how you would solve an exponential expression if you could get two bases on either side that have the same basis. We can set their exponents equal to one another. Cheers.